Hey everyone, in this physics video we are focusing on free fall. We're going to learn what that term means and then see how it applies actually to some physics equations we've already learned. This is the start of our physics that's moving away from horizontal, like left to right, east to west motion, and incorporating some slightly more complicated vertical motion. All right, but before we get into that, a very brief history lesson. Okay, back in around 380 BC, so well over 2,000 years ago, a guy named Aristotle, very famous philosopher even during his own time, okay, one of the first to really start philosophizing, thinking about the way our world and our universe works. And he came up with the idea, the conclusion that heavier things fall faster than light things. And that is not a bad conclusion to make, not only at the time, but even like now in our classrooms or at home. If you picked up a bowling ball and a feather and you drop them, the bowling ball, the heavier thing, would fall faster. It hit the ground first. Even a pencil will fall faster than, say, a piece of paper. All right. So Aristotle wasn't totally out of his mind for thinking about this. And that's how most people thought about the way our world works when it came to falling objects until really the time approximately around Galileo. Now, there's some debate whether it was actually Galileo. I'm sure there are some smaller philosophers, early scientists who came up with these ideas both before and after Galileo. But Galileo, 1564. So well over 1,500 years after Aristotle, start really thinking, him and contemporaries, that, well, you know, Aristotle's maybe not crazy, but there's this thing known as air resistance. There are these forces that might impede falling objects. And Galileo and then his contemporaries, they showed scientifically that it's actually the fact that if you could discount air resistance, if you could remove any forces, anything that gets in the way, all objects fall at the same rate. Now, it's actually a bit contentious whether Galileo actually did scientific experiments, if he specifically did. Others, again, his contemporaries and those shortly thereafter, maybe even before, certainly did do experiments, ways to remove air resistance. And yeah, he found this big idea, and this is what we know today. Yeah, there's air resistance, and it kind of mucks up some of our experiments. But if we could ignore it, all objects, regardless of their mass, fall at the same rate. So when we are talking about free fall, we are, one, going to be ignoring air resistance, okay? And therefore, what that means is all objects fall at the same rate, the same increase in speed as they're falling. Okay, so this idea of free fall, what it means is, or what it refers to as, objects under the influence of Earth's gravity. We're going to learn about gravity in a later video, okay? It's a force, there are some details, we'll get there. But right now, all you need to know, and of course you know this being a being on Earth, is that gravity pulls things down. Gravity causes things to accelerate downward. If something is in free fall, we're only considering an object just under the influence of gravity, meaning we'll ignore air resistance. It does exist. It's pretty small, even in real life, but we'll just assume that it doesn't exist unless stated otherwise. We'll also assume if we say there's an object under free fall, it hasn't like hit a table, or it's not falling through water, which also provides some resistance. So it's just like moving through the air, just falling, of course, but we're even ignoring the air part of it. Okay? And because Galileo and his contemporaries, and of course ever after, realized that gravity applies the same free fall to all objects regardless of mass, things under the influence of gravity have a constant downward acceleration. It doesn't change based on the object. It is constant. So objects that are in free fall have a constant acceleration, and we call that constant acceleration g. G because it's so fundamental, because it is constant anywhere here on Earth. All objects fall at the same downward acceleration known as g. Okay? Well, what does that look like? If you remember, we had a video looking at vectors and what that means, how like acceleration shows a change in velocity. So in this part right here, and I'm going to move my head because it's a little bit in the way of the diagram. I move it like right there. That's good. If I drop an object, okay, I pick up a rock, I hold it like this over a cliff, and I just release it. Well, it starts at rest, right? My hand isn't moving. If I'm holding my rock or my pen right now, it starts at rest. When I first release it, it starts moving pretty quickly, but for a moment, right when I let go, it starts off with zero velocity, And then as it falls, it's accelerating. It's going faster and faster and faster. The acceleration because of free fall, because of gravity, is 9.8 meters per second squared down. So what does that mean? In the beginning, I said this rock starts off with 0 velocity. 1 second later, it has gained a velocity of 9.8. Remember, this means you gain a velocity of 9.8 meters per second every second. That's what meters per second squared means. After 2 seconds, another 9.8 gets tacked on. 3 seconds, another 9.8. For each of these times, I'm adding 9.8 velocity. Not distance, velocity. So of course, what this means in layman's terms, when you drop things, they speed up. And all objects speed up. They all accelerate at this same value. Remember from our last video, I can't plug in this word down into my calculator. So if we follow convention, which is usually things moving up is the positive direction, because gravity, of course, is tugging things downward, g is 9.8 meters per second down, or negative 9.8. Now, if this was Mr. Thrasher's own diagram, and I normally say up is positive, I would technically, if I was keeping these as velocities, be putting in little negatives. Okay, because if upwards is positive, downwards is negative, and obviously these objects are all falling downward with a constant acceleration, 9.8 meters per second squared down, or negative 9.8. Okay, now think of what I've been saying several times now, a constant acceleration for all objects. Have we learned equations for constant acceleration? Absolutely we have. So my last slide is really us revisiting equations that we've already learned. Let's take a look. We've spent a good amount of time, and let me move my head again back over here. Oh man, a little jarring. We've learned equations for constant acceleration. They're here on the left. I haven't used this label before, but we've always been focusing up until now on things moving horizontally. So here's that equation, v equals v naught plus a times t. X equals x naught plus the initial velocity plus 1/2 at squared. These three equations should look familiar. There's just one little difference. I am labeling them with an x. We didn't have to worry about that before because it was only x. But now we're going to start looking at motion in the vertical direction. In math class, what did we call the vertical axes of a graph? That's known as the y-axis. So now we have equations for things moving horizontally and for things moving vertically. And for things moving vertically, it's a constant acceleration. And in vertical motion, we label that g. Again, g equaling negative 9.8 meters per second squared, assuming you're taking up as being positive. So now over here on the right, it's the same three equations, but I'm just putting in this little y subscript to show that it's in the vertical direction. So it's the exact same three equations as before, but couple of things just to point out, not that they're really different, but things that are maybe looking a little new in these equations. Acceleration in the y direction is called g. So before we were just labeling it as a, and of course like a spaceship and an airplane and a bicyclist could have different accelerations. But for free fall, it's always the same, g. So I've replaced a with g. This is how you're going to see it on the AP Physics 1 equation sheet in most textbooks. Okay? And also, normally we were using like delta x for displacement. It's still displacement, but in the vertical direction, again, we use the letter y. So the exact same three equations, you use them the same way, but you'll notice some different subscripts or some different labels, all right? These two things in red, don't forget these. Mr. Thrasher always uses upwards as being positive. So when I use these equations, I plug in a negative 9.8 because that acceleration is always down. If it's in free fall, we're not talking about someone throwing it in the air or rockets blasting it upwards. We're just talking about gravity pulling it down. That means it's always negative 9.8 for that acceleration. Okay? Now, we're also, unless it says otherwise, if it just says like, Bill dropped a ball, calculate whatever. Unless it says otherwise, just assume there's no air resistance. And that, again, means you can use these equations. You plug in negative 9.8. One more thing, just real quick. The AP Physics 1 test, they will actually allow you, and they'll even put it on the equation sheet, they'll allow you to use the value of, say, negative 10. 9.8 is very close to 10. You could on the AP exam, and you could if you're in my own classroom, use 10. Just know your answers might look a little different than my own because I always use 9.8. Okay, but the AP test and other textbooks sometimes allow you to round up a little bit. So you could use 10, but I will always be using this 9.8. That's the more precise version of that acceleration due to gravity. Okay, but that's it. It's the same equations, just now applied to things moving vertically. I'm done. Thanks a lot for watching.